Hello students, welcome to AIMS India online classes. This is a chemistry session. Here we are discussing about chemical bonding chapter. Okay. In this session, especially we are going to say about a special concept from the chemical bonding chapter. That is hybridization. The concept which was proposed to explain about the bond shapes and bond angles in the molecules. That is hybridization. Let us say about this concept in this session. The concept of hybridization of atomic orbitals was proposed by Pauling for the first time. The shapes of molecules and bond angles can be explained in terms of this hybridization concept. The phenomenon of intermixing of orbitals of the same atom which have nearly same energy to form equal number of new orbitals of equivalent energy is known as hybridization. So we need to understand one thing here. It is a hypothetical concept which is proposed to explain the bond angles and the shapes of the molecules. So in this, it is explained here the phenomenon of intermixing of atomic orbitals of the same atom, which are having nearly same energy, and thus they form new atomic orbitals which are having equivalent energy. This phenomenon is called hybridization, and those new orbitals formed with equivalent energy are called as hybridized orbitals. Okay, so this happens within the same atom. Before the bond formation, the orbitals of an atom they intermix each other and they form the new orbitals the same or equivalent energy. Those orbitals are called hybrid orbitals, and that phenomenon is called hybridization. Okay. Rules of hybridization. The orbitals of one and the same atom only participate in the hybridization. Yes, we said this. Atoms of different elements they do not hybridize. They do not participate in the hybridization. Orbitals of the same atom they participate in the hybridization and they result in the formation of hybrid orbitals. But orbitals of different atoms they do not hybridize. And the energies of the hybridizing orbitals must be equal or they should be nearly equal. Then only those orbitals will participate in the hybridization and they result in the hybridized orbitals. The number of hybridized orbitals formed will be equal to the number of atomic orbitals which are participating in the hybridization. Okay, how many orbitals participating in the hybridization, the same number of hybridized orbitals will be formed. The hybrid orbitals are symmetrically arranged around the nucleus of the atom so that they have maximum stability. So to be with the maximum stability and with less repulsions, these formed hybrid orbitals will be arranged around the nucleus of the atom in the symmetrical position. The angle between any two adjacent hybrid orbitals is same, and generally the bond angle in the molecule or ion is also same. A hybrid orbital can have maximum of 2 electrons with opposite spins. So just like the normal orbitals, these hybridized orbitals also can accommodate maximum of 2 electrons with opposite spins. Hybrid orbitals form only sigma bonds. Okay, these hybridized orbitals will participate only in the formation of sigma bonds. That means end-to-end overlapping only. These hybridized orbitals they do not participate in the pi bond formation. They do not form pi bonds. That means they do not overlap lateral. They overlap only end to end or head on end. Head on overlapping only they participate and thus they form only sigma bonds. These hybridized orbitals they do not form pi bonds. Now let us see the types of hybridization. What do you say hybridization means here? The phenomenon in which orbitals of an atom, they overlap each other or intermix each other to form new and with the same energy orbitals. That phenomenon is called hybridization, and those newly formed orbitals are called hybridized orbitals. So, based upon the type of atomic orbitals involved in the mixing, based upon the type of orbitals participating in the hybridization, this hybridization can be classified into different types. They are Sp hybridization, Sp2 hybridization, Sp3 hybridization, Sp3D hybridization, and Sp3D2 hybridization. In this way, based upon the number of orbitals and the type of orbitals intermixing, the hybridization can be classified into these many types. See, once these all Sp, Sp2, Sp3, Sp3D, and Sp3D2. There are different kinds of hybridizations. Now let us see about these kinds of hybridizations one by one. First, let us go through Sp hybridization. The mixing of one s orbital and one p orbital to give two equivalent hybridized orbitals is known as Sp hybridization. Okay, when one s orbital and one p orbital of an atom, they intermix each other to form two equivalent energetic hybrid orbitals is known as Sp hybridization, and here the equal energetic orbitals so formed are called Sp hybridized orbitals. This is one Sp hybridized orbital, this is another Sp hybridized orbital. In that way, two equivalent orbitals are formed with the same energy. These orbitals are called Sp hybridized orbitals, and that phenomenon is called Sp hybridization, in which one s orbital and one p orbital are intermixed. Okay. Now these two Sp hybridized orbitals have linear shape. So these two are arranged in this format for that atom. So in the linear shape they are arranged and with an angle of 180 degrees between them. Okay, see here it is a 180 degrees bond angle because they are in the linear position. Each sp hybrid orbital has 50% s character and 50% p character because one s orbital and one p orbital they intermixed here in the formation of these sp hybridized orbitals. That's why the s character is 50% and p character is 50% for these sp hybridized orbitals. Sp hybridization is also called as diagonal hybridization. Okay. Let us see now some examples for the molecules having this sp hybridization. First, to explain this, let us consider the formation of beryllium difluoride molecule, BEF2 molecule. In the BEF2 molecule, the central atom is beryllium. So its atomic number is 4, and the electronic configuration of beryllium atom in its excited state is 1s2, 2s1, 2p1. Because in normal and ground state, beryllium configuration is 1s2, 2s2. Isn't it? It is normal configuration of beryllium. But in the excited state means by gaining certain amount of energy, the electrons present in the valence shell or valence orbital will be jumped into higher orbitals, higher vacant orbitals. So here beryllium has 2 electrons in its 2s subshell or 2s orbital. When it gains certain amount of energy from outside, one electron jumps into 2p subshell. Okay, then its configuration becomes now 1s2, 2s1, 2p1. It is called excited state electronic configuration of beryllium. See, this is the excited state electronic configuration of beryllium. Okay, one electron jumped from 2s orbital to 2px orbital. In the excited state, beryllium atom 2s and 2px orbitals intermix to give two equivalent sp hybridized orbitals. See here, this 2s orbital and 2px orbital. These two are having unpaired electrons. These two orbitals will intermix each other and forms two equivalent sp hybridized orbitals like this. Okay. Now, these sp hybridized orbitals will bond split in the bond formation. In another case, if you see the electronic configuration of fluorine atoms, their atomic number is 9 and their configuration is 1s2, 2s2, 2px2, 2py2 and 2pz1. So if you observe the configuration, it has one half-filled 2pz orbital. Okay. This half-filled 2pz orbital of two fluorine atoms overlap with sp hybridized orbitals of beryllium atom in their axis to form two sigma bonds. They are called two Spp Sigma Bonds. So in this way. So they are sp hybridized orbitals of beryllium, two sp hybridized orbitals. These will overlap with the 2pz orbitals of fluorine atoms on both ends, and thus they form two covalent bonds. Those are called sigma bonds, and they are also known as here spp overlapping sigma bonds, because the sigma bond is formed due to the overlapping of sp hybridized orbital of beryllium and p orbital of fluorine. That's what is called spp sigma bond. So beryllium fluoride molecule has two spp sigma bonds and its shape is linear. BF2 molecule so formed has linear shape like this, and the bond angle in BF2 molecule is 180 degrees. Now, let us see about Sp2 hybridization. The intermixing of one s orbital on two p orbitals to form three equivalent sp2 hybridized orbitals is known as sp2 hybridization. See here, one s orbital and two p orbitals. These two are intermixed together to form three equivalent hybridized orbitals. This each hybridized orbital is called Sp2 hybridized orbital. Okay. Now these three are called Sp2 hybridized orbitals. And we can understand one more point here. How many orbitals are participating in the hybridization? The same number of hybridized orbitals are formed. See here, one s orbital and two p orbitals means totally three orbitals are intermixing, and hence three hybridized orbitals are formed. Okay. And here each hybridized orbital is called sp2 hybridized orbital, and that phenomenon is called sp2 hybridization. Okay, the three sp2 hybridized orbitals are directed towards the corners of an equilateral triangle with an angle of 120 degrees. See here, they form an equilateral triangle angle. Each will be forming 120 degrees angle with other. Each sp2 hybridized orbital has 33.33% s character and 66.66% p character, because it is formed by the intermixing of one s orbital and two p orbitals. That's why s character is 33.33 and p character is 66.66. Example for the molecules having sp2 hybridization. Let us see with example formation of boron trifluoride molecule. In this molecule, the central atom is boron. In boron trifluoride, the central atom is boron. The electronic configuration of boron in its excited state is 1s2, 2s1, 2p2. Normal electron configuration of boron is 1s2, 2s2, 2p1. This we know already. But before bond formation, certain amount of energy is gained by boron and its valence electrons, and one electron from its s orbital, it jumps into vacant p 2p orbitals. Okay, thus it becomes 1s2, 2s1, 2px1, 2py1. This is a electronic configuration of boron in its excited state. Actually, this electron should be here in the ground state, but when it gained electron energy, this jumped from s orbital to vacant to p orbital. That's why it became now 1s2, 2s1, 2px1, 2py1. So if you observe, there are three unpaired electrons, one in each s orbital, 2px orbital and 2py orbital. Now, in the excited boron atom, one 2s orbital and two 2p orbitals intermix to give three equivalent sp2 hybrid orbitals in this way. So here this 2s orbital and these two 2px and 2p orbitals. These three intermix each other and form three equivalent sp2 hybridized orbitals. So 2px orbital and 2py orbital, two p orbitals and one s orbital. These all are intermixed together to form three equivalent hybridized orbitals which are called as sp2 hybridized orbitals, and this phenomenon is called sp2 hybridization. Now, this each hybridized orbital is called sp2 hybridized orbital. This is one sp2 hybridized orbital. This is one sp2 orbital. This is another sp2 hybridized orbital. Okay. In the formation of BF3 molecule, that is boron trifluoride molecule, three sp2 hybridized orbitals of boron overlap with half-filled 2p-z orbital of three fluorine atoms in their axis to give 3 sp2p sigma bonds. So in this way, we know in the earlier case also have seen about fluorine. It has one unpaired electron or half-filled atomic orbital, that is 2p-z orbital. When this hybridized boron it approaches three fluorine atoms, each sp2 hybridized orbital of boron overlaps with 2p-z orbital of fluorine atom. In that way, they form three sigma bonds like this. See here, this is a sp2 hybridized orbital of fluorine. This is overlapping with 2p-z orbital of fluorine. So by this overlapping, they are forming one sigma bond. This sigma bond formed here, it is called sp2p sigma bond because it is formed by the overlapping of sp2 hybridized orbital of boron and 2p-z orbital of fluorine. That's why it is called sp2p sigma bond. In that way, three sigma bonds are formed in this boron trifluoride molecule. BF3 molecule so formed has trigonal planar structure. In this way, the structure of the boron trifluoride is being. So trigonal planar shape it is called. And here the bond angle is being 120 degrees. Some other examples for the molecules having sp2 hybridization, or it is called ethylene C2H4. Ethene or ethylene it is called. In this also there will be sp2 hybridization for the carbon atoms. And boron trichloride, just like the boron trichloride molecule also it is having sp2 hybridization on its central atom boron. Okay, that's about sp2 hybridization. Let us see another kind of hybridization, that is called sp3 hybridization. The intermixing of one s orbital and three p orbitals to give four equivalent sp3 hybridized orbitals is known as sp3 hybridization. See here, in this hybridization, one s orbital and three p orbitals, px, py, pz orbitals. These four orbitals are intermixing to form equivalent four new orbitals or hybridized orbitals. These newly formed hybridized orbitals are called sp3 hybridized orbitals, and this phenomenon is called sp3 hybridization. Why it is called sp3 hybridized means it is formed from one s orbital and three p orbitals. That's why these are called sp3 hybridized orbitals. Now it is one sp3 hybridized orbital. This is another sp3 hybridized orbital. This is one more sp3 hybridized orbital. This is another. So they are three-dimensionally arranged in the space. These are called sp3 hybridized orbitals. Sp3 hybridized orbitals are directed towards the four corners of a regular tetrahedron. The angle between the two sp3 hybridized orbitals will be 109 degrees 28 minutes. Okay, four sp3 hybridized orbitals will be arranged in the space in the shape tetrahedron, that is called regular tetrahedron shape. Here, between any two sp3 hybrid orbitals, the bond angle will be 109 degrees 28 minutes. It is pronounced like this: 109 degrees 28 minutes. In this, each sp3 hybridized orbital has 25% s character and 75% p character because it is formed from one s orbital and three p orbitals. That's why s character is 25%, whereas p character is 75%. Example for the molecules having sp3 hybridization, let us see here. Let us try to understand this sp3 hybridization formation in the methane molecule, CH4 molecule. If you see, the central atom in this CH4 or methane molecule is carbon. We know its atomic number is 6 and its normal configuration is 1s2, 2s2, 2p2, isn't it? But in the excited state, one electron from s orbital, it jumps to vacant 2p orbital. Thus, its electronic configuration in the excited state will be 1s2, 2s1, 2p3. That is nothing but 1s2, 2s1, 2px1, 2py1 and 2pz1. In this way, carbon is having 4 half-filled atomic orbitals in its excited state. Now, in the excited carbon atom, one 2s orbital and three 2p orbitals. These four orbitals intermix to give four equivalent sp3 hybridized orbitals. Okay, these are four orbitals which are having single electron. These four will intermix each other and form four equal energetic hybridized orbitals. This each hybridized orbital is pronounced as sp3 hybridized orbital. This is one sp3 hybridized orbital. This is one. This is one. This is another one. In this way, four equal energetic sp3 hybridized orbitals are formed. This phenomenon is called sp3 hybridization. Okay, and we can understand here how many atomic orbitals are participating in the hybridization. The same number of equal energetic hybridized orbitals are being formed. Okay, see here, one s orbital and three p orbitals are intermixed. Totally four orbitals are intermixed and hence resulted in the formation of four hybridized orbitals. Okay, so in the formation of methane molecule, four sp3 hybridized orbitals of carbon overlap with one s orbitals of four hydrogen atoms in their axis to form four sigma bonds. So here, in this way, carbon in its excited state getting four sp3 hybridized orbitals. So when it approaches hydrogen atoms, each sp3 hybridized orbital of carbon overlaps with one s orbital of hydrogen atoms, four hydrogen atoms, and thus results in the formation of four sigma bonds. This is the way. So this is a sp3 hybridized orbital of methane and it is s orbital of hydrogen. So these two overlap here and thus they result in the formation of a covalent bond which is known as sp3 s sigma bond. Okay, this is called sp3s sigma bond. In that way, four sigma bonds are formed in the methane molecule. So this methane molecule so formed has regular tetrahedral shape. Tetrahedron it is called. Tetrahedral shape commonly it is called. Okay, the bond angle in this methane molecule is being 109 degrees 28 minutes between any two hydrogen atoms. So here the bond angle is 109 degrees 28 minutes. And some other molecules which are having this sp3 hybridization or it is called here ethane. Already we have seen here methane molecule. In the same way, ethane molecule, C2H6 it is. In this also, carbon atoms are having Sp3 hybridization. In the CCl4 molecule, which is called carbon tetrachloride molecule, in this also, the central atom carbon is having Sp3 hybridization. And some other molecules like water, ammonia also, they have Sp3 hybridization on their central atoms. Okay. Now let us see another hybridization, that is Sp3 dehybridization. In this, the intermixing of one s orbital and three p orbitals and one d orbital, totally five atomic orbitals, they intermix each other to form five equivalent sp3d hybrid orbitals. This is known as sp3d hybridization. Okay, what is happening here? One s orbital, three p orbitals and one d orbital. These will intermix each other to give five equivalent sp3d hybrid orbitals. So this phenomenon is called sp3d hybridization, and thus formed five orbitals are called sp3d hybrid orbitals. Okay, in this way, see, one s orbital, three p orbitals and one d orbital. These all will intermix to form five equal energetic hybridized orbitals, which are called as sp3d hybrid orbitals. Okay, now let us see one example for the molecule which is having this sp3d hybridization on its central atom, that is a PCl5 molecule. In this PCl5 molecule, the central atom is phosphorus. In that, it has its excited state electronic configuration as, we know its atomic number is 15. It will be having 3s1, 3p3 and 3d1 excited state electronic configuration. Actually, its electronic configuration, the normal condition is 3s2, 3p3, isn't it? But in the excited state, one electron from its s orbital jumps into vacant d orbital. Now totally it is having 5 orbitals with the single electron occupation. Here 3s1, 3px1, 3py1, 3pz1 and 3d1, 3dz1. Okay, 3dz square 1. In this way, 5 atomic orbitals are there with the half-filled configuration. These five atomic orbitals intermix each other to form equal energetic 5 sp3d hybrid orbitals. Okay, now phosphorus is having 5 sp3d hybrid orbitals. And when it approaches the chlorine atoms, each chlorine atom is having one p orbital with the half-filled configuration, that is 3pz orbital is being with a single electron. So when these phosphorus and chlorine approach each other, each sp3d hybrid orbital of phosphorus overlaps with 3pz orbital of chlorine, and thus they form 5 sp3d sigma bonds. Okay, in that way PCl5 molecule is formed, and its molecular shape will be trigonal bipyramidal shape. So these three are in the trigonal planar shape, and above the plane there is one chlorine, below the plane there is one more chlorine. So this is called, from the top one pyramid shape is there, from the bottom there is one more pyramid shape. That is why it is called trigonal bipyramidal shape. PCl5 molecule, or the molecules the sp3d hybridization will be having a trigonal bipyramidal shape. Within the plane, the bond angle will be 120 degrees, and above and below the plane, the bond angle will be 90 degrees. Okay, this is about sp3d hybridization. Let us see another kind of hybridization, that is sp3d2 hybridization. In this, the intermixing of one s orbital, three p orbitals, and two d orbitals, totally 6 orbitals, they intermix each other, and they result in the formation of 6 equivalent sp3d2 hybrid orbitals. This phenomenon is known as Sp3 hybridization. Okay, thus formed equivalent energetic orbitals are called Sp3 hybrid orbitals. See here in this way, one s orbital, 3p orbitals, 2d orbitals, totally 6 orbitals. They intermix each other and they result in the formation of 6 equal energetic hybridized orbitals. Here each hybridized orbital is called Sp3 hybridized orbital. In that way 6 hybridized orbitals are formed. Okay. Now let us see an example for the molecule having this Sp3 hybridization. That is SF6, sulfur hexafluoride molecule. In this molecule, the central atom is sulfur. We know the atomic number of sulfur as 16 and its configuration will be 1s2, 2s2, 2p6, okay, 1s2, 2s2, 2p6, 3s2, 3p4 actually. In the ground state, it will be having 3s2, 3p4 valence electronic configuration. But in the excited state, this sulfur will be having excited configuration as instead of 3s2, it becomes 3s1, 3px1, 3py1, 3pz1 and 3p, sorry, 3d x square y square 1 and 3d z square 1. Means totally it is having 6 half-filled atomic orbitals. Actually it will be having 3s2, 3p3, 3d1 configuration, isn't it? But in the excited state, one electron jumps from 3s orbital to 3d orbital. So in that way, sulfur is getting 6 atomic orbitals with half-filled configuration in its valence shell. Now, these 6 orbitals of sulfur intermix each other and form 6 equivalent sp3 hybridized orbitals. Now, when this sulfur with the sp3 hybridization approaches fluorine atoms, each sp3 hybridized orbital of sulfur overlaps with 2pz orbital of fluorine atom, and thus they result in the formation of sigma bonds. Each sigma bond can be pronounced as here sp3 p sigma bond, sp3 sigma bond, because it is formed by the overlapping of sp3 hybridized orbital of sulfur and 2pz orbital of fluorine. This is called sigma bond and it is pronounced as sp3 sigma bond. In that way, sulfur is forming 6 sigma bonds. Okay, its molecular shape is called square planar bipyramidal shape. So 4 sigma bonds are there in the same plane along with the sulfur. One fluorine is above the plane and the other one is in the below the plane. So it is called square planar bipyramidal shape. And within the plane, the bond angle will be 90 degrees and above and below the plane also will be 90 degrees. So this is a molecule which is having sp3 hybridization. So this is about the concept of hybridization, which explains the shape and bond angles of the molecules based upon the hybridization. Okay, thank you for watching our video. Please subscribe our YouTube channel Aims Today for latest updates and recorded videos. And please visit our website aimstoday.in for another information regarding online classes, quizzes, live worksheets, do-it-yourself activities, English classes, reasoning classes, and even coding classes.